This is Harbin. Welcome to our first video notes of semester 2. We're going to look at 4 main ideas here. Hopefully you look at these 4 things and even write them down and see if you can do them when we're done. There's a lot of connections in the book. Please read sections 10.1 and 10.2. Oh, look, there's some bonus. All right, so dimensional analysis. Sounds scary, but it's not. It's when we use conversion factors that are equalities to cancel out and get to units. So here's an example. One liter equals 1,000 milliliters. That's an equality. And so if we want to use this as a conversion factor, we could say 1 liter for every 1,000 milliliters, or we could say 1,000 milliliters for every 1 liter. And then this equality turns into these 2 conversion factors, conversion factor, conversion factor. When you're doing dimensional analysis, the units guide you. You cancel out what you want to get rid of, and you get to what you want to keep. We'll practice. Make sure you put the correct number next to the correct unit in each conversion factor. Okay, so if I'm going to put the unit of liters up here, I got to put the number 1 with it because 1 liter. And if I put the unit of milliliters down here, I got to put the number 1,000 with it because that's where it comes from this equality. Okay, so if you have a dozen things, you'll have 12 things. So we can write 2 conversion factors for that. We can say 1 dozen for every 12 things. Or we could say 12 things for every 1 dozen. Okay, so these are called conversion factors. And it's use the equality. It has to be true. And we talked about this one on the other page. So 1 liter equals 1,000 milliliters. So there's 2 conversion factors you can write for this. And you have to be able to take any equality and turn it into a conversion factor to do dimensional analysis. Okay, so let's do it. We have 212.3 milliliters, but we want to know how many liters that is. So we start with the given, 212.3 milliliters. That's what we were given. We want to convert it into liters. So we have to put the unit of milliliters on the bottom, the unit of liters on top. So we're setting up a conversion factor, and we have to make this true. So it's true that 1 liter equals 1,000 milliliters, so I have to put the number 1 with liters and the number 1,000 with milliliters. And then this unit and this unit cancel out, and we're left with liters. And we have to do 212.3 divided by 1,000, so we have to put 2,123 liters. Okay, notice the units cancel out, and you're left with the unit you wanted to get to. That's what we wanted to get to. And this was our conversion factor. Conversion factor. Right, let's try one that's a little more complicated. Hey, how many school days do we have until summer vacation? About 88. We want to know how many minutes that is. So we start with the given, 88 days. And we want to convert it into minutes. Now, I don't know a direct relationship between days and minutes. You might, but I do know that every day has 24 hours. So I'm using that as a conversion factor. But I'm still not done because I want to convert it to minutes. So I have to cancel out hours and change to minutes. And then I have to make this a true statement. So I say every 1 hour has 60 minutes. Look what happens to days. Look what happens to hours because top and bottom cancel. We're left with minutes. How many minutes is that? Wouldn't you like to know? Well, I have to do 88 times 24 times 60. And I get 126,720 minutes. Wow, we better get busy. That's not a lot of time left. Okay, so what are we doing this for? Dimensional analysis is going to help us solve problems with chemistry. Chemistry deals with small pieces of stuff. Those particles are called, if they have a charge, that small particle is called an ion. If it's an ionic compound, that small particle is called a formula unit. So the smallest piece of something is a representative particle. All right, write that down, representative particle. What represents an ionic compound? Formula unit. What represents a molecular compound or a covalent compound? Molecule. What represents an element? Most elements are represented by atoms. That's their smallest part. But some elements, NOF, brewery. Oh, I forgot the F. 1, 2, 3, 4, 5, 6, 7. Those are represented by molecules. And then So these kinds of particles, formula units, molecules, atoms, molecules, are called representative particles. So what's the smallest part of this? Well, this is a metal and a nonmetal, so this is ionic compound, so it's a formula unit. Formula unit. That's what represents the ionic compound. What about this? Nonmetal, nonmetal, represented by a molecule. Ooh, look, it has charge. So this thing that represents that is represented by ions. This is a molecule. All right, I want you to try these other ones, these two, and then we'll talk about them. All right, so you try. You try. Is there one more? Oh, yes, there is. You try these three. Okay. All right. So all these particles are small. Let's get an idea of how small atoms and ions and molecules are. Well, here's a cell. You know you can't see a cell without a microscope. Cells are really small. But inside this cell, there's this many atoms. That is a lot of atoms in something that's already small. Let's take it even smaller, right? See this grain of salt right there? Let's talk about that one. So on average, there are this many formula units in that one grain of salt. Okay, so sodium chloride. There are this many repeating sodium chloride formula units in that tiny grain of salt. That's a stinking lot. Okay, so let's talk about a lot. When you have a lot, we don't really count them. We just count a bunch of them together. So you know, I buy a ream of paper when I need paper, or a gross of bottle rockets, or a dozen donuts. So a ream of paper is 500 sheets. A gross of bottle rockets is 144 bottle rockets. Woohoo! 4th of July! And a dozen donuts is 12. So why do we put a large number of things in a group? Because it's easier to count them that way. So what do we use in chemistry to count our molecules and atoms? We use a mole. I said it, a mole. So how many things are in a mole? Well, this many. 6.02 times 10 to the 23rd. All right, that is a lot of stinking particles in a mole. That's a huge number. Huge, 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 huge. So, why do we use this many things in a mole? Because atoms are so small and tiny. Now, we need to count a lot of them at a time to even be able to see them. Okay, so a mole is really important because it lets us count really, really, really small things by grouping them together in a large group. Okay, this number, 6.02 times 10 to the 23rd, it's called Avogadro's number. All right, so what's a mole? Oh, look, it's a mole. And you're probably thinking that looks like a potato. But guess what? It looks like a mole. See, there's the eyes and there's the nose. Oh, it's a smiley mole. It just needs some little hands, right? Oh, look, now it's really a mole. A mole is a unit of measure. And we use it in chemistry. So let's talk about how many of what are in one mole. So we have 1 mole. If we have 1 mole of cookies, how many cookies would we have? Well, if you say 6.02 times 10 to the 23rd, you'd be correct. Now, that's a lot of cookies. I think I ate that many over Christmas break. Just kidding. All right. How many, what's in 1 mole of water? Well, water's H2O. So it's 6.02 times 10 to the 23rd. What's molecules? Because it's a covalent in 1 mole of H2O. In 1 mole of H2O, there's that many molecules. What about helium? Well, helium is represented by atoms. Helium equals atoms, so 1 mole of He equals, if you're saying 6.02 times 10 to the 23rd atoms of He, you'd be right on. Okay. What about calcium fluoride? Well, calcium fluoride is CaF2, periodic table cancel charge. So these are represented by formula units. So if we had 1 mole of calcium fluoride, guess what? We'd have 6.02 times 10 to the 23rd formula units. Oh, look, I abbreviated it for you. That's the nice way to abbreviate it. Okay. How about this? How many times would you like to see methane bubbles on fire? A mole of times? So 1 mole equals 6.02 times 10 to the 23rd times. Okay, so 1 mole equals Avogadro's number of representative particles. So how do we relate this to chemistry? Well, in the lab, we usually use mass to measure our stuff. So if you had a whole bunch of atoms or molecules together, we could weigh them and figure out how much a mole is. So we want to know how much is in the mole using mass. We got to use the mass from the periodic table. So what this number on the periodic table represents is atomic mass units. And so there's 12.011 atomic mass units in carbon. And then if we want to know how much is in a mole of carbon, we just change the AMUs to grams. Okay, but that's just for an element. What if we have a compound? Well, we change we take the number from the periodic table, 14.01, and I just rounded it to 2 decimal places. And there's one of them in NO, so that's 14.01. And then we say oxygen is 16.00, and there's one of them in NO, so 16.00. And so we get 1, 0, 0, 3. Now, what does this mean? It means 1 mole of NO has a mass of 30.01 grams. Right? So that means that these are molecules. Right? So that means there's Avogadro's number of molecules in 1 mole, and then that all of those molecules would weigh, 1 mole of those molecules would weigh 30.01 grams. Look, it's carbon dioxide. So how do we know how much is in a mole of carbon dioxide? Well, there's 1 mole of 1C in there, so 12.01. And then oxygen, there's, from the periodic table, 16.0, but since there's 2 there, we need to multiply by 2. Oops. 32, hey, come back, 32.00. So we find out that 1 mole of carbon dioxide is going to weigh 44.01 grams. Okay, so that means that this is a molecule. If we have Avogadro's number of molecules and we have a mole, and we can weigh them out and find out that's 44.01 grams. So we can use that in lead. All right. So we got to go to the periodic table if we want to know how much 1 mole of aluminum sulfate weighs. Now, in this one, we have 26.98 times 2, because there's 2 aluminums. And so we get 53.96. Right? And then that's for aluminum. And then what about sulfur? Well, there's a sulfur there, but there's 3 of them. So I have to say 32.07. Look, I rounded it to 2 decimal places. That rounds up. And there's 3 sulfurs, and that equals 96.21 grams. Okay, what about oxygen? Oxygen. Okay, there's 4 here times 3. So we have 16.00 times 12. That's a lot of oxygen. There's 192. Oh, this is 96. Who did that? 192.00 grams. All right. But then I have to add that all together to get the total mass. 342.17. So what does this mean? It means that 1 mole of aluminum sulfate would weigh 300. I did my numbers backwards again. Who does that? No, how did 342.17 grams of aluminum sulfate? This is called the molar mass. Molar mass is the mass of 1 mole. How do you figure it out? Well, the periodic table tells you how much 1 mole of atoms weighs. And so you add those all together to figure out how much 1 mole of molecules weighs. Now, in this case, it's 4 millionths. If it's an ionic compound, 4 millionths again. So we have nitrogen is 14.01 times 2, 28.02. And then hydrogen, be careful. Hydrogen is 1.01. Remember to, I didn't put it on here. You round up to 2 decimal places. And then 4 times 2 is 8 hydrogens. So we have 8.08. Carbons in this 4 million units, 12.01 times 1. And then oxygen. And 16.00. That's times 3. So we have 48. Then I have to add it all together. When I add that all together, I get 96.11. Now, what does that mean? Well, it means that 1 mole of ammonium carbonate is going to be equal to 96.11 grams of ammonium carbonate. So, that means that if I had 1 mole of this substance, then there'd be Avogadro's number of formula units, and that would weigh 96.11 grams. Okay. So in chemistry, we count by weighing because the molar mass of anything is the mass of 1 mole. So 1 mole, or Avogadro's number of anything, is equal to the molar mass from the periodic table. Okay, the mass of 1 mole. 1 mole of anything has the same number of particles as a mole of something else. So if we can weigh it, we know how many are in it, Avogadro's number, but each particle has a different mass. So molar mass is going to be different for every substance, but what's the same about it is the number of molecules or atoms or formula units. You have to remember that 1 mole has Avogadro's number of particles in it. So I'm going to say representative particles. The kinds of representative particles we can have are atoms, molecules, or formula units, right, depending on what kind of particles we're talking about. And 1 mole equals the mass in grams from the periodic table. So here are 2 things that you have to remember in order to understand the mole. That 1 mole has Avogadro's number of things in it, and 1 mole is going to weigh the mass in grams from the periodic table. So let's see if we can start converting. So we talked about dimensional analysis at the beginning. In this case, we're trying to find grams given moles. Right. Oh, wait, what's this? MOL. Someone forgot the E? No, the abbreviation for mole is MOL. Doesn't that make your life easier? You get to drop that E. All right, so now we start with the given 0.32 moles of Fe. We want to change it into grams. So conversion factor time, you put moles of Fe on the bottom, grams of Fe on the top. Now it's moles and grams, and on the last slide we found out that 1 mole equals a mass in grams from the periodic table. So we have to put 1 mole, and we go to the periodic table and find out the mass in grams of iron is 55.85. Moles are going to cancel. And then when you do 0.32 times 55.85, you find out that this is 17.87 grams of iron. Notice what I did. I canceled out the moles of iron, and I turned it into grams of iron. And so that's how much about a third of a mole would weigh. Okay, how many moles? So find moles given grams. Okay, grams of what? Hydrogen gas. And don't forget that hydrogen gas is H2 because it's a diatomic element. So we start with the given 43.8 grams of hydrogen gas. And we need to change grams of hydrogen gas into moles of hydrogen gas. How do I know? Given, find. Given, find. And we're going to end up with moles of hydrogen gas, which is what we're looking for. How do we fill in this equality? Well, we know that 1 mole of hydrogen is going to, we go to the periodic table and find, be equal to 2.02 grams of hydrogen. How do I get that? 2 times hydrogen's mass. So 2.02 grams for 1 mole. Grams cancel grams. 43.8 divided by 2.02 gives me 21.68 moles of hydrogen gas. All right, can we keep converting? You betcha. This time we want to find grams, okay, given moles. What are we given moles of? Carbon dioxide. You have to know the chemical formula, CO2. So how much would this many moles weigh? Well, you start with your given 3.25 moles of CO2. Don't you love that abbreviation? It takes a whole half a second off your time here. We want to cancel out moles of CO2 because that was our given. We want to change it to our find grams of CO2. All right, anytime we have moles and grams in a conversion factor, we need to go to the periodic table and get grams. We did this one earlier, so I remember 44.01. You can look back if you want. And that equals 1 mole. So I used my equality that 1 mole equals the mass from the periodic table of the substance. Moles cancel moles, and then multiply 3.25 times 44.01. When I take 3.25 times 44.01, I get 143.03 grams of carbon dioxide. One more conversion. A scientist. Ooh, that could be you. needs 586.39 grams. So this is what we're given. This is what we're given of iron 3 oxide. We want to find moles of iron 3 oxide. The key to this problem is knowing the chemical formula of iron 3 oxide. So this means that this iron is a +3 charge, oxygen is a -2 charge, iron symbol is Fe. So we have Fe, let's see, O, -2, O, -2, O, -2. It's Fe2O3. So I'm going to leave the rest of this problem for you guys to do, and we'll check it in class. Okay? All right, so let's review. Woohoo, review. Moles are groups of particles or anything that have Avogadro's number of representative particles, 6.02 times 10 to the 23rd. That's a large group because atoms and molecules and formula units are very tiny. What are representative particles? Representative particles, formula units could be, molecules could be, atoms can be. It's the smallest thing that represents the substance you're looking at. If you want to know the molar mass of a substance, you got to go to the periodic table and get it in grams, and you find out that 1 mole of your substance equals grams of your substance from PT, from the periodic table. Okay, always go through moles when you're converting. Okay, 1 is the number that goes with moles when the other unit is grams. So in a conversion factor with moles and grams, or moles in grams, anytime it's moles, moles are 1, and you have to go get the grams from the PT. Okay? Also, conversion factors help us solve problems, so let the units guide you. Read chapter 10, peeps. Do a bonus if you want to do a bonus. And so these 4 things. Do we know what the mole is? Molar ratio we'll get to in the next video notes. Molar mass and mass, what it means, okay? And then how to use conversion factors for dimensional analysis. And then the mole concept in dimensional analysis, because we can change mass and moles into each other now. Okay, peace out. Have a good one.